So starting on number 1, we have a rock, mass m, slides up a ramp with a speed v naught, reaches the bottom of the ramp. So it is v naught at the bottom of the ramp. The ramp is at an angle theta to the horizontal, as shown. Coefficient of kinetic friction between the rock and ramp is mu. The distance d, it slides up the ramp before stopping vertical distance h above the bottom of the ramp. Derive an expression for the force of friction exerted on the rock. So an expression for the force of friction on this rock. Well, there's a couple of things here. So we've got distances, we've got we've got heights, right? It's a vertical distance is a height. There's a mu, but if it asks us for force of friction, right? Force of friction as related to velocity and distance. So we've got velocities and heights. We also have distances and forces. Velocities and heights related to distances and forces, right? This means conservation of energy. When you have forces and distances, that means that you can do work. Right? Work equals Fd. But here's kind of the new thing. Looking at our equation sheet, we have work is whatever force is parallel to the displacement. But if they're not parallel, it's Fd cosine theta. And it's this second part of this equation that's really the focus of this lesson. It's the second half of this equation, this Fd cosine theta. When do we use Fd cosine theta? Or when do we use work is equal to force parallel displacement? So Fd cosine theta, and this is the angle. Theta is always the angle that's between force and displacement. So it's the angle that's between the force and the displacement. In this case, because it's the force of friction, so it's this force of friction that's working here, as the block slides up the ramp, what direction is friction? Against the motion down the ramp. What direction is displacement? Up the ramp. Are those lines parallel to each other? In physics, we have, when things point the same way, parallel, or if they point opposite directions but along the same line, we call it anti-parallel. These are same direction but along the same line, anti-parallel, which is good enough to say, or cosine of theta goes away, because essentially here theta between those is 180 and cosine of 180 is -1. What this tells us, since it's -1, this tells us that friction does negative work, right? The negative part. All that means is that when the two lines are anti-parallel to each other, it's negative work, right? Force is opposite of displacement, negative work. So that's just another way to look at everything that we've done before. And because they're along the same line as each other, we don't have to worry about this cosine. So half of the struggle with doing energy when there's angles involved is figuring out when is there an angle in the problem that you don't need versus when is there an angle in the problem that you do need. That's what our problems are going to continue doing as we go through them. So friction does negative work, but we can get rid of this cosine here. All right, so then we have conservation of energy and work being force times displacement because the cosine of theta can kind of go away. So we can start with our general conservation of energy expression. Energy initial plus or minus work equals energy final. What kind of energy do we start with? Kinetic. Do we do positive or negative work? Negative work, because force is opposite displacement, so negative work. And I'll just make a subscript. Oh. Okay, PA. I'll make a subscript just to remember that this is work done by friction. Energy final. Well, we're raised to height h, so there's UG. And then it stops at that height h. So there's no kinetic energy anymore. So there's our expression. Someone's having fun on the PA. All right, 1/2 mv0 squared minus, and then work of friction, right? Work we can spread out into FD cosine theta, but we said that that cosine theta goes away, so force of friction times displacement. And then UG is mgh. Remind me, what's our goal in this case? Force of friction. So we need force friction equals. So when I see this force friction right here, I need to not substitute for force friction. Right? I need to solve for that. Don't substitute for force friction. Even though they give us mu, right? You could do mu Fn, but we don't need it. So I'm gonna add force friction and then subtract, add force friction D, subtract mgh to both sides, so 1/2 mv0 squared minus mgh equals force friction times displacement. So then I can divide both sides by displacement and get force of friction equals 1/2 mv0 squared minus mgh all over displacement. You could stop right there if you wanted to simplify, and I'm just gonna reverse distribute a mass out of the numerator. So this is just the simplified version. You do not have to do the simplified version. This is totally fine, or this is totally fine. If you were to see like an answer key or on a multiple choice, this is what you would see on a multiple choice, but this would be totally fine if you're on like a free response or something like that. All right, there's number 1. Questions so far? Okay. No. A 5-kilogram crate is on a horizontal frictional surface. A force of 40 newtons is exerted on the crate at an angle of 37 degrees to the horizontal, as shown in the figure above, causing the crate to slide to the right. After the crate slides a distance of 10 meters, the box reaches a final velocity of 7.75 meters per second. How do we know what approach to use? Forces and distances. That's your dead giveaway. We're going to be using conservation of energy with work. Plus, we start with velocity, we start, it never specifically says. We start at rest. Sorry, I should say that. But then we end with a final velocity. So that's your giveaways, forces and displacements. Part A, though, says calculate the normal force between the crate and the surface. So this is backing up 1 unit to all of our forces at an angle. So in backing up 1 unit, all right, if you're asked to calculate a force, first thing we've got to do, free body diagram. So there's going to be a normal force from the ground, force of gravity pulling it down. That force with which we are pulling, which they've just labeled as F, and then force of friction because it is a frictional surface. Why is force of friction straight left instead of against our pole? It moves straight right, friction opposes sliding. But that free body diagram doesn't really help us out a whole ton, does it? So remember our process, keep everything that's straight along the axes. Then let's break up the angled force into its components, right? The force, that pull force in the x-axis, that pull force in the y-axis. And since we are given the angle theta to the horizontal, that's going to be F cosine theta. That's going to be F sine theta. That's just our regular stuff to the horizontal axis. Normal force. Which axis do we need? Y-axis. So we'll do the sum of the forces in the y-axis, but we can say, right, in the y-axis that's 0. It's only moving left and right. It's not going to be accelerating up and down in this case. So we can just use Newton's first law. We can say Fn and the force in that y-axis are both up. Upward forces have to equal the downward forces for Newton's first law to kick in. Right, Fn is what we want to find. We can't plug in for it. Here's your reminder. Normal force can never be equal to force of gravity if there's an angle involved. It's never equal to force of gravity if there's an angle involved. And then Fy is F sine theta. Force gravity is mg. So then subtract that F sine theta from both sides, and we can plug in some numbers. 5 kilograms, g is 10, minus F is 40, sine theta, theta is 37 degrees. So I can do 5 times 10 minus 40 sine 37, and I get 25.9. I am going to round that to 26 newtons. I'm going to round it because we're given 37 degrees, which means, oh, they want us to have a, right, it's a 3, 4, 5 triangle. So whole numbers. So our normal force, 26 newtons. All right, there's part A. Questions so far? All right, then part B, calculate the coefficient of kinetic friction between the crate and the surface. So this is where, all right, coefficient of friction, mu leads us to force of friction being equal to mu times Fn if it's kinetic. So we're trying to relate forces based on velocities and distances. That's where we get this conservation of energy. So then conservation of energy, right, it's E naught plus or minus work equals E final. We start with 0 energy, starts at rest, at its lowest height. Then in the x-axis, so here's where work kind of gets a little tricky. All right, we've got F, this force helping us. So plus work done by that pull force. But then we have force of friction acting against us. It's hurting us, so minus work done by friction. Every individual force is an individual work. You got to figure out for each of them, is it plus or is it minus? And then energy final, it's just kinetic energy. So work done by pulling, well, that's where we can do that FD, and then since work is FD cosine theta, this force is not horizontal, but the displacement is horizontal. So there's an angle between them. We need this FD cosine theta. So this is using work at an angle when there is an angle between the force and the displacement. That's when we use FD cosine theta. But friction. So friction is backward, displacement is forward. Are those in the same line as each other? So we just need FD, where this is force of friction. There's no cosine theta because they're along the same line. And the negative is because they're in opposite directions. Equals kinetic energy 1/2 mv squared. Well, we have almost everything able to plug in, just not this force of friction yet, because we need coefficient, so we've got to plug in mu Fn. So I'm going to do FD cosine theta minus mu Fn times that displacement equals 1/2 mv squared. Oh, it's almost like you were asked to solve for normal force for a reason. By the way, all 4 of these problems are taken straight from AP. You're at the point now in the year where I get to teach you concepts using AP level problems. It's kind of fun.
Sorry to interrupt.
You good?
Have you seen the lasers and boulders for this lab?
No, sorry. All right, so we can plug in now. Force is 40, displacement is 10, cosine of 37 degrees, minus mu is what we're trying to solve for. Normal force 26, displacement 10, 1/2, mass 5, final velocity 7.75. That gets squared. So I get 319.5 minus 260 mu equals 150. So mu equals 0.65. That's a longer question. That's definitely a long question. Most questions aren't this long. That would be something that would be about half of an entire free response question with the way they just asked you that. And on the AP test, there's only 4 free response questions. So that's 1/8 of the AP free response length right there. Questions on number 2 before we move on? All right, number 3, it is then. Number 3, we've got a conveyor belt. Ramp has length 7 meters, is inclined at 20 degrees with respect to the horizontal. It's used to move objects from one location to another location. When an object is placed on the conveyor belt, it travels up the incline at a constant speed of 1.5 meters per second. A motor is used. The mass of the objects that are placed on the conveyor belt are varied. Suppose the motor breaks. Suppose the motor breaks. And a person must push an object of mass 30 kilograms from the bottom to the top. The person can exert a force of 150 newtons on the object parallel to the incline. What is the approximate amount of work that the person does to move it to the top of the incline? Assume friction is negligible. All right, what are we asked for? Work. As a reminder, and I've kind of glossed over this the first couple of questions, so here's your major reminder. When I say, what is work? What do I want your first response to be? Change in energy. So let's try that. What is work? Change in energy. But there's an alternate way to calculate work if you're given a force and a displacement. So how do we calculate work when we're given force and displacement? F d cosine theta. And as a reminder, anytime we are using this equation, we have to figure out, because this is the angle theta between the displacement and the force. We have to figure out what that angle is. So if a person pushes a box up the ramp, what direction is the force? Up the ramp. What direction is the displacement? Up the ramp. What's the angle between those? 0, which means cosine theta goes away. Because if you take cosine of 0 degrees, it gets you 1. Multiply anything by 1, it's the same as what it was. So this is one of those questions where they give you an angle that you don't need. And that's exactly why they do it, is because they know that you see this equation, that you see theta, that you see you're given an angle, and you just plug in automatically. This is a multiple choice question that I pulled from. I just took away the answers. And guarantee one of those answers is F times D times cosine of 20 degrees. But instead we need cosine of 0. All right, so what's our force? 150. What's our displacement? 7 meters. Okay, if you multiply those, you get 1050 units. Joules. Done. So some of these problems do go pretty fast. It's just in recognizing when do you use FD, when do you use FD cosine theta. Questions before our last problem? All right. A student strikes a 0.5 kilogram block. Remind me, what does strikes mean? It means you have V naught, so V naught's greater than 0, but it means no push force. That's what that word strikes means. It means it starts with an initial velocity, but that there is no push force. Strikes a 0.5 kilogram block, so it slides up a ramp with an initial velocity of 8 meters per second. Frictional forces are considered non-negligible. Okay, so we have friction. Coefficient of friction is 0.2. Top of the ramp, block has been displaced vertically by 1.2 meters. and has traveled 2.4 meters along the surface of the ramp. As a brief side note, I've seen plenty of problems where they don't give you 2.4 and they only give you 1.2 and 30 degrees. But with the angle, with that angle and that height, could you find the displacement? Yeah, it just makes it a slightly longer problem. What speed will the block be traveling when it reaches the top of the ramp? Okay, what speed will the block be traveling when it reaches the top of the ramp? Well, we have coefficient of friction, which is basically force of friction. We have a displacement. We have a vertical displacement, also known as height. And we have a velocity. Velocities and heights, what does that tell us? Conservation of energy. Force and displacement, what does that tell us? Work. All right, so we know our starting point. E naught plus or minus work equals E final. Being able to do these and identify where to start is the most important part of this course. It's also the hardest part because we have a lot of tools you can solve problems with. All right, starts with a velocity. All right, that's why the strikes is important. So it starts with some amount of initial kinetic energy. And then there is work done by friction. Is work done by friction positive or negative? Always negative. And it turns into gravitational potential energy as it goes up the ramp, right? And speed at the top. That means that there is now also some final kinetic energy. All right, 1/2 mv naught squared minus force of friction times displacement mgh 1/2 mv final squared. And that v final is what we're looking for. There's only one thing we can't quite plug in for as of yet. We're gonna have to do a little side quest for force of friction. All right, if we draw our free body diagram for an inclined plane, normal force off the ramp, force of gravity into the ramp, frictional force down the ramp. But that's not super useful. We've got to do our component free body diagram. And remember, inclined planes, you tilt your axes. So it's normal force off the ramp, force friction down the ramp, FGX, down the ramp, FGY, into the ramp. So when I want my force of friction equals mu Fn, what can I use to find Fn? FGY equals mu FGY. So I can say my force of friction is mu mg, and inclined planes are weird, and you can see y cosine theta. So I'll take this and plug it back in. 1/2 mv naught squared minus mu mg cosine theta times displacement mgh plus 1/2 mv final squared. Oh, look at that. There's a mass in every term. Side question. Why do we not have negative work for FGX? If I'm using gravitational potential energy, that means that gravitational forces are internal to the system. That Earth is part of the system. So gravity or its components are internal forces and do not go under work. It is a weird thing to realize. It's a weird thing to realize. I just wanted to make sure to specifically point that out. All right, we can plug in some numbers. 1/2 V naught is 8 minus mu is 0.2, g is 10, cosine of 30 degrees, times the displacement is 2.4, g is 10, h is 1.2, plus 1/2 v final squared. I get the left side is 27.8 equals 12 plus 1/2 v final squared. So 15.8 is 1/2 v squared. And I get final velocity 5.63 meters per second. All right, there's our last question there. Questions on any of our problems?